Hello, everyone. Welcome back to the AAS YouTube channel, and we're going to continue the video series on discussing articles that are in the AAS journals. And I am delighted today to have Daryl Seligman with us. Hey, Daryl.
Hey.
Say a little bit about you.
Yeah, well, thank you for having me. I'm really excited to be here, even during this coronavirus crisis. So I am a graduate student at Yale University right now, working. My advisor is Professor Gregory Laughlin. I'll be graduating this year, and I'm moving to the University of Chicago next year, where I'll be at the T.C. Chamberlain Fellow in the Geophysics Department.
Oh, that's cool. Great. Excellent. Yes. Excellent. Assuming one is allowed to fly and move around.
Exactly. I'm really hoping that I could still move in September.
Yeah, cross fingers.
Yes.
Well, that's awesome. So today we are going to walk through a really lovely article titled "On the Anomalous Acceleration of I-1 2017 Oumuamua," and I apologize for any bad pronunciation my Hawaiian may have there, but that's where we are. So I'm going to go ahead and share our screen here, and we will start walking through the paper. Preview. And if you see that okay, Daryl, go ahead and take it away.
Yep, that's great. All right, so just a little bit of background about this paper. So the reason this was motivated, so this has actually more than a year after Oumuamua was discovered. So just some background is that Oumuamua was discovered as the first interstellar object to ever be seen passing through the inner solar system. So this was a couple of years ago now, in October 2017, that it was discovered, and it had a hyperbolic trajectory. So it was certainly unbound from the solar system. And there are a lot of weird things about Oumuamua. The first seemingly weird thing was that it had no cometary activity. So generally, we think that comets and asteroids, the difference between comets and asteroids, that comets, you'll see the long, beautiful cometary tails come out. That's icy volatile material that's sublimating and outgassing. And you're seeing micron-sized dust particles that are entrained in the outflow that are reflecting sunlight. But Oumuamua, what everyone expected about interstellar objects were that these kind of interstellar objects that were they're basically planetesimals that form around other stars. If they're loosely bound to their stars or form very far out from their solar systems, then to be ejected by something like a giant planet, you would expect that there should be a lot of volatile icy material in them. So everyone expected that the first interstellar object should have a clear, distinct cometary activity. So Oumuamua came through, and it was passed very close to the Earth. It was detected as it was leaving the solar system, but there was no coma. It was just a point source in all images. And so that meant that there was very strict limits on the outgassing of volatile species that was coming off it, or at least very strict limits on the number of micron-sized dust particles in that outflow, if it was there.
Right.
So then the weird thing is that several months later, after it gets discovered, there was a Nature letter that was published announcing that there was a non-gravitational acceleration in the trajectory of Oumuamua. So the non-gravitational acceleration, it was a 30 sigma significant detection. And it meant that there was no single hyperbolic trajectory that could match Oumuamua's astrometric position on the sky. So there
what was the magnitude of that acceleration? Do you happen to know?
Well, so the best fit was an acceleration that continuously pushed away from the sun.
Okay.
That was strength of about 1/1000th of the solar gravitational acceleration.
Okay. So
for solar system comets will outgas and have non-gravitational accelerations. That's a strong outgassing non-gravitational acceleration, but not an unprecedented one. But what is strange is that there was no coma seen along with that. And now, another weird thing about Oumuamua was that if you look at the light curve variations, Oumuamua exhibited about a factor of 12 in brightness variations.
Okay.
So we could actually go, if we just quickly go to figure 3, we'll come back to this later, but this shows just some of the So if you look at the top left panel, these are the brightness variations of Oumuamua over time during the first couple of days of high cadence photometric variations that were taken. And what you're seeing is that this is a log scale, so this is magnitude. Mm-hmm. And so Oumuamua is changing in brightness by about a factor of 12 there. And this is happening periodically. So this was interpreted as Oumuamua being very elongated and tumbling. So if it's very elongated, what's happening is you're seeing head-on versus edge-on projections of light that's being reflected from the sun. And so when it's a brightness maximum, you're seeing an edge-on view from the Earth. And when it's brightness minimum, you're seeing a head-on view. But to get something like a factor of 12, you need at least 6-to-1 elongation. And first of all, that's strange because we've never seen something in the solar system that has a factor of 6-to-1 elongation. Right. But then we realized this paper was motivated that there's something else that's weird. So the idea is that if you accept that Oumuamua is an elongated object, so something like 6-to-1 in aspect ratio, either like a cigar or like a pancake, then if you have an outgassing event on the surface of that asymmetric object, then what will happen is that unless the jet from the outflow organizes itself so that it's always pointing along a principal component, then the outflow will provide not only a change of linear momentum and change the acceleration, or provide the non-gravitational acceleration that was observed, it should also provide change in angular momentum.
Right.
So that jet should torque it up, and you should observe its spin period changing. Yes. Especially because Oumuamua is a kind of a small object, and the best fit non-gravitational acceleration, the magnitude of it, which we were asking about, is very strong. Right. So the fact, if you look at the top right panel here, that's just a periodogram. So you're seeing there's a clear 4-hour peak there, or about roughly 4 hours. So that's saying that over several tumbling timescales while Oumuamua was observed, remember it was actually observed for longer than what we're showing. This is just the first couple of days of observations. Right. Oumuamua was not spinning up. Okay. So we were motivated to write this paper because after the non-gravitational acceleration was announced, we realized that if this might be a potential first order inconsistency between the non-gravitational acceleration being interpreted as cometary outgassing. Because remember that cometary outgassing is going to act the exact same way as the best fitting force. That is a cometary jet that's exploding in the direction of the sun, pushing Oumuamua away from the sun. Mm-hmm. So there might be the first order inconsistency is that there's the cometary jet interpretation of the outgassing and the lack of a secular spin up that was observed in Oumuamua. So we wanted to take a closer look at the spin dynamics that get induced from an outgassing event to see if this inconsistency, if we had kind of a more sophisticated outgassing model, if we could rectify this inconsistency. Okay. So if you go up to figure 1 now. Yes. Okay. Right. If you can see that figure on the left there, basically what this is showing, so it's actually kind of cool. So we created this with a computer graphics software. Mm-hmm. And the reason we did this was what this computer graphics software will do is allows you to place objects like an ellipsoid down and then place a camera and a sun down and a light source. Mm-hmm. But the camera and the light source are analogous to the Earth and the sun. So what you can do is place down Oumuamua, the Earth and the sun, and the computer graphics software will get all of the ray tracing exactly correct if you were to place a camera or telescope on Earth. So with this computer graphics software, you can recreate exact representations of synthetic observations of what Oumuamua would have looked like under an outgassing model.
Okay, so those XYZs, those are the principal axes, is that right?
So these are the body axes of Oumuamua.
Yeah.
And these are going to rotate. So what we're going to do is we're going to consider how Oumuamua will, a 6-to-1 ellipsoid will move dynamically under the action of a jet that exerts a change in angular momentum. And so what you're seeing here, the first idea is just if you have a jet that is stagnant, so a jet that's sitting in one place, it will change angular momentum and it will rapidly spin up Oumuamua. However, what we wanted to look into is if we have a kind of more realistic cometary jet model, that is one in which the jet is actually able to move across the surface, which you observe in comets, then what happens? So if you see here, the sun is placed, you can't see the sun in the image, but it's placed that way, exactly. And so the sun is shining on Oumuamua, and what we do is we say, allow the jet to explode. We do two assumptions. Allow it to explode at a point normal to the surface, and always in the direction of the sun.
Okay.
What'll happen then, so you see there's two lines, that's just an example of a normal to the surface and where we would put the jet if the sun was positioned as in this schematic. And so what will happen is that jet is going to apply a torque. That jet is going to explode at that point, produce a torque, change the angular momentum, but as it'll spin Oumuamua, but as Oumuamua spins, the jet can then move.
Roll around,
and
yeah.
The jet will then move to the new substellar point, is what you call it. But that's just a point where the sun is maximally shining. And this is a physically motivated model because the point where this Oumuamua is getting maximal solar radiation is where those subsurface volatiles are getting heated up the most. And that sublimation of volatile material is what's driving the outflow. So this is certainly an idealized model, and we're going to idealize it one step further. But the reason for doing this is just to get kind of physical intuition for the problem. So what we're going to do is we're going to do the problem in 2 dimensions and completely analytically. Okay. So in 2 dimensions, was that a question, Frank?
No, go ahead.
So if you do it in 2 dimensions, remember, this is with the caveat that this is completely idealized, but just to get intuition for what this substellar point tracking jet is going to do. In 2 dimensions, we're only going to consider rotations in the XY plane.
Right. Okay.
About the Z axis.
Yes. Okay.
And so without going through the kind of messy math of it, as long as you demand that the jet always tracks the exact substellar point and induces a torque there, this system kind of beautifully reduces to a 1 degree of freedom Hamiltonian, which is shown in equation 4 here. And, for people who are, not as familiar with Hamiltonians, a Hamiltonian is just a statement of the conservation of total energy in the system. So what we're saying is that the total rotational energy in the system can be described in this Hamiltonian form. And so the derivation is not that interesting, but what is kind of cool, if you look at this equation, you've got big theta. Big theta is the spin or the angular momentum, and little theta is just basically you can either think of it as Oumuamua's rotation from the sun, or you could think of it as just where the jet is along the surface. And the reason this works is that, this might seem a little bit counterintuitive because I'm saying that you can describe this system with a Hamiltonian, which is a statement of the conservation of energy. But at the same time, I'm saying that there's a jet which is exploding off the surface and changing how fast Oumuamua is spinning. So the reason this works is that the jet, because we formulated it in this kind of idealized way and it's tracking the substellar point and pushing at the sun, it's acting like a conservative force. So you can treat it as it's just like a potential energy. There's actually almost a direct physical analogy, and that's of a pendulum. So what a pendulum will do is basically you hold the pendulum kind of up at its highest point, that's maximum potential energy. And that's the maximum energy. That's when the jet is kind of at the pole. And that's maximum potential energy stored in the jet. And then what will happen is as the pendulum swings down, the jet's the equivalent of the jet moving to the center of Oumuamua. And what that'll be, that then is like Oumuamua. So you basically got the potential energy is stored in the jet, like the force of gravity on the pendulum. And then the kinetic energy or the rotational energy is just how the pendulum or Oumuamua swings. And what's kind of cool about this Hamiltonian is if you look at figure 2, that's a phase space diagram for this Hamiltonian. And so the phase space diagram, what's cool about this is that this phase space diagram is, it's not exactly the phase space diagram of a pendulum, but it's very similar to that. So this is what's cool about this Hamiltonian is it's almost exactly the Hamiltonian for a pendulum.
So if this was a pendulum, right, the phase space diagram of a pendulum like this includes the case where the pendulum swings over.
Right.
And so you have phase space that's sort of inside, if closed contours, if you like, and then there are the contours outside of that, right? Which
that's exactly right.
To a complete rollover.
That's right. And so what you're seeing here, just to explain what's going on here, the x-axis is that little theta, which is saying the rotation, the instantaneous rotation of Oumuamua, or the position of the jet along the surface. Big theta, remember, is the spin. So exactly like you were saying, Frank, is that you've got a clear separatrix. So these black lines are the level sets of the Hamiltonian, or just what the dynamics will do under a constant total amount of H, or total amount of energy. So a system that starts on one of those black lines will just rotate around, move around the black level set, but never leave it. So you've got the separatrix, which I think you can see is just delineating the kind of cat's eye structure to the separatrix right in between the curves that close around themselves and the curves that move off the page. Inside that separatrix, those level sets are going to be, as you said, are going to be just the librations or rocking back and forth. And then outside of that is going to be the full circulation. So all of the black lines above the separatrix are showing basically what will happen if Oumuamua has enough rotational energy to start to keep going over its head. And then the background color is showing you what you can do is take the Hamilton's equations, integrate them through time, and get the period of the oscillations that are induced for each of these level sets. And the point here is that even though right around the separatrix you get a little bit of change in period, if you're sitting on one of the level sets, the period never changes. So wherever you are in phase space, I mean, Oumuamua was tumbling, so it was most certainly in a circulating regime. If this model is correct or somewhat correct, you always, because the jet is able to rock back and forth, even though Oumuamua tumbles, it's never going to spin up under a jet that's able to track the substellar point. So that means that if this model is correct, then the constant spin period is, well, first of all, it's completely consistent with the outgassing interpretation of Oumuamua. But more than that, there's an amazing result that pops out. And so with a pendulum is completely described by 3 parameters, and that is the strength of gravity, which is pushing down, the length of the pendulum, and the frequency or the period. So in this analogy, so the math actually works so that that actually works for Oumuamua. Then if this kind of idealized model is correct, you have measured the period of Oumuamua via the photometric variations.
Yes.
You have also independently from that measured the strength of the non-gravitational acceleration via the astrometric position.
Effectively G, yes.
That's effectively G. So then using those to second order in the aspect ratio, that gives you a dynamical size constraint on Oumuamua.
Yep.
And that size constraint is about 100 meters, which is exactly in line independently with what you would get, which other authors have gotten by just saying, let's assume Oumuamua has a solar system like albedo, take the brightness that it was, or average brightness, and estimate a size.
Yeah, okay.
So, and the question now is just so that's a very, very clean, nice result, the dynamical size constraint, if this model is correct. So totally admit right now that the outgassing model is completely idealized. So you've got, there's two issues with it. There's the one is that it's in 2 dimensions, and the other is that you have a jet that immediately tracks the substellar point. And both of those are not really realistic. We know those aren't exactly the right assumptions. So what we did is then we do a full 3-dimensional tumbling analysis. So you do this, you don't need to do, the 1 degree of freedom Hamiltonian is messy enough. So we did this just with a computer simulation. And this is literally just doing rigid body, all it is rigid body dynamics.
Body dynamics, love it.
All you do is find a point on the surface, calculate a torque, change the angular momentum, change your rotation matrix, and then do it at the next time step.
Yep.
And what you do here, then what that will allow for is the full 3-dimensional tumbling. So the question is, once you include the full 3-dimensional tumbling with the jet that's able to move across the surface, will Oumuamua spin up or not? So Frank, if you could show that video now that we were showing.
Sure, okay, I'm gonna stop sharing this one, everyone.
In this video that we're gonna show, we actually...
So we're gonna share a YouTube video.
In the video that we're gonna show, we use that same...
Go ahead.
We use that same computer graphics software to render exactly the scene that you would see of Oumuamua under the dynamical outgassing model. So what you're seeing here, you start Oumuamua tumbling. This is an Oumuamua, I think this is a 9-to-4-to-1 ellipsoid. That's just kind of a fiducial model. We ran several simulations with different geometries, but the 3 body axes that were shown in the last figure 1 are shown here, and they move with Oumuamua. What you're seeing, this blue line, the blue arrow that's mobile, that's the jet. So that is what's happening here. The sun is placed behind us now. So we're sitting on Earth, and the sun is behind us, illuminating the object. Got it. And then the jet is mobilizing on the surface to exactly track the substellar point. And then what's happened is as it explodes in real time, it's exerting a torque, and that's making the angular momentum change, and it's making the tumbling of the body change. And what you're seeing, so in the plot that's in the top left, that's the flux that you would observe seen from Oumuamua on Earth. So we're using this computer graphics software to get the ray tracing exactly correct. And this is an example where we have albedo variations on the surface.
I was going to say, there's a modeled, a modeling.
Exactly. So I'll go into that later, but we did many experiments where we changed the amount of albedo variations on the surface to see if you could get more moderate aspect ratios. Okay. Variations. Okay. But the point of this is to show that, this video is something like 10 minutes long, so you don't have to watch the whole thing, but the point is that Oumuamua never spins up. So even when you introduce the full 3-dimensional tumbling, Oumuamua still exhibits that 2-dimensional pendulum-like dynamics. Okay. I think we can go back to the paper now. Okay. We'll stop. And one thing that's kind of was surprising about this and is kind of amazing is that in the 2-dimensional case, you've reduced the problem to a 1 degree of freedom Hamiltonian. Then we do the 3-dimensional tumbling analysis that is, in some sense, doesn't know about the Hamiltonian and doesn't know about the 1 degree of freedom problem. And although it is able to tumble around all 3 axes, it's able to rotate around all 3 axes, you only get one period in the resulting light curve. So that's telling you that in some way, because of the symmetry of the problem, the three degree of freedom problem has effectively reduced to a 1 degree of freedom problem. And that's not obvious that's not trivial. So that's a kind of weird dynamics problem that I think kind of popped out of this that I still am kind of amazed by. But anyway, so what we show in this figure, so the top two panels are showing the real data. So that's Oumuamua's light curve variations between October 25th and 28th. And on the right is the periodogram. Okay. And then these next 3 panels are showing those same 3 things, but for our full 3-dimensional tumbling analysis with 3 different outgassing, with 3 different geometries. So we have a 9 to 4 to 1 geometry, a 10 to 1 to 1, that's more like a very thin needle or cigar, and the 10 to 10 to 1 is more like a pancake.
Right.
And we ran these for different geometries, but the point was we weren't fitting the light curve here. What we wanted to do was just qualitatively get 2 features, the 2 defining features, correct. So the 2 features we want are the kind of factor of 12 in brightness variations.
Okay.
So just showing that Oumuamua can go from bright to dim. And then the lack of spin up. So you want that 4-hour spin period. And you're seeing that all the models are effectively able to do this. So that 4-hour spin, I mean, the main thing is that 4-hour spin period in the periodograms on the right. And that's telling you that even under the full 3-dimensional, the full jet-induced outgassing model, you never get a spin up. So that's basically telling you that the non-gravitational acceleration would be consistent with the outgassing.
Right.
And not only is it consistent, but it'll give you a dynamical size constraint.
Right.
Now, the other caveat I said I didn't mention is that the assumption that the jet perfectly tracks the substellar point is very idealized.
Sure.
Also, the perfectly symmetric body or ellipsoid is also idealized. So what we did was we did many experiments. We talk about it in the text of the paper, but what we did was we did experiments, dynamical experiments, where we added both time delays, varying amounts of time delays to the position of the jet. The reason for doing this is to model effectively a thermal inertia in Oumuamua. So that's just, all that's saying is that it takes, there should be a little bit of a lag because it takes time for the heat from the sun to travel to the interior and heat up volatiles. So we did this, and we stochastically forced the position of the jet. Okay. So the reason for doing this is twofold. One is just to model kind of the fact that you're not going to have a perfectly subsolar tracking jet anyway. So it could come out of, different crevices on the surface of Oumuamua, but also that stochastic forcing also mimics the effects of asymmetries of the body itself. And what we found was that even we did many experiments of both varying levels of stochastic forcing and thermal inertia, and you still see the same pendulum-like oscillations. Mm-hmm. So what's cool about this is that even when you relax the idealized assumptions, you basically get the pendulum-like oscillations.
Cool. So if we, is Oumuamua solved?
I wouldn't say that. I'd say that there are still mysteries about Oumuamua.
Okay, such as?
I mean, the lack of a coma is still weird. So that's a limit on the number of micron-sized dust particles that were entrained in that outflow. Okay. So for this to work, you basically have to say that there were, if there was dust in the outflow, it maybe was dominated by larger dust grains that wouldn't have showed up in the optical. Now, there have been some comets that had very slight comas or lack of micron-sized dust particles, but that's certainly a weird thing. And now, we have what is it? I'm losing track of time, but pretty recently we had this fall, the second interstellar object came through. That was Borisov, and that was discovered by an amateur.
Yep.
So that's pretty exciting. But what's kind of amazing about Borisov is that Borisov is acting exactly like what you would expect an interstellar object or comet to act like. So
okay, awesome. So
it has a big coma. It clearly has volatiles. It's clearly some exo Oort cloud object that was scattered out by a giant planet, and it's acting like a solar system comet. And we've been doing observational campaigns of Borisov to see what the composition of that object is, and it's quite similar to solar system. The composition is quite similar to solar system comets. So if you look, Michelle Bannister, led a paper that we have out. It's on the archive now, but we had an ongoing campaign observing it with MUSE and the TRAPPIST telescopes, and that shows some nice. We have figures there showing the evolution of the carbon chain species in Borisov's outflow over time. But effectively, Borisov is acting very much like you would expect an interstellar comet to act like. So what Borisov does is it gives a nice context to Oumuamua because it highlights how, just as typical as Borisov is, Oumuamua is a total oddball. So it's highlighting all of the weird things about Oumuamua. And so it seems like these two objects are drawn from distinct populations. And what we would imagine, what we really need to do is find more of these objects. And
I was just going to go there. So if you were to look in your crystal ball here toward the future, are you seeing a golden age of interstellar interlopers coming into our solar system that we detect?
Absolutely. So just in a couple of years, the LSST, or now renamed Vera Rubin telescope, is going to detect many, many more of these objects. Mm-hmm. So not in this paper actually, but the first paper I wrote about Oumuamua, we talked about the feasibility of doing an in situ observation to something like Oumuamua, or doing an interception mission to an interstellar object. And in that paper, what we did was we took objects just like Oumuamua, so synthetic objects that were the same brightness as Oumuamua, and did Monte Carlo simulations of a galactic population of interstellar objects like Oumuamua coming through the solar system, normalized by the number density that's kind of implied, the galactic number density that's implied by Oumuamua. And then with these Monte Carlo simulations predicted how many objects like Oumuamua LSST is going to detect every year. And that figure is something like on the order of 10. So our predictions were somewhat optimistic, but our optimistic predictions are roughly 10 objects like Oumuamua per year once that comes online.
Awesome.
And then, I won't go through that paper, but the upshot was you've got a wait time of roughly about 10 years before finding one that comes close enough to the Earth that we could feasibly send an interception mission to. So I think that's really the future, is that we're going to start detecting many, many more of these objects. And just with the detection of Oumuamua, we had a high number predicted to be detected. So with Borisov now, I think it's promised that we're going to detect many more of those. And then, it is likely that in the near future, we might be able to do an interception mission to one of these objects, which would tell us a lot more and definitely solve mysteries.
Absolutely. And that is an awesome place to take an end on this one. So very cool. I'm going to say that if folks would like to contact Daryl about doing an interceptor mission to an interstellar object, you know how to get in touch with him. And he's open to you contacting and talking about this very exciting frontier is where this is headed, I do believe, over the next decade. So this is cool. So with that, I want to thank everyone for listening in on this one, and we'll see you on the next one. Thanks, Daryl.
All right, thanks so much.